All right, you guys. I'm going to take a break from physics for a few days to give you another math lesson. And this one is on the subject of tensors. Um, and this is really important for research in liquid crystals because tensors are an important way of describing how things depend on orientation or describing the orientation of three-dimensional objects. And the science of liquid crystals is all about orientation order. So this is something that we have to talk about. I want to begin by giving you some propaganda, some ideology of why we work with tensors before I get into the details of how we do it. And the ideology is really based on a fundamental principle of physics, which is that nature doesn't care about me, right? That nature just does whatever it does, and the predictions that I, as a physicist, make about nature cannot depend on any arbitrary decisions that I make, any arbitrary choices about my point of view. Right? So one important example of that has to do with units. Right? That what we say about nature cannot depend on what system of units we decide to work in. So, to tell you an example, when we first moved to Ohio, our older son was in high school, and when winter came, he would say, how can you expect me to go outside? The temperature is less than my age, right? And so, of course, I knew what he meant, right? I knew he meant that the temperature in Fahrenheit was less than his age in years, right? But the statement by itself is meaningless, right? You can't say is an age bigger or less than a temperature, right? That's not true or false. It has no meaning because it depends on what your choice of units is for age and for temperature. Um, Another thing like that is coordinate systems. Right. So when we start to describe physical properties in terms of some coordinate system, that can be a useful tool, but the statements that we make cannot depend on the choice of coordinate system. If they do, then they are meaningless in the same way that comparing an age with a temperature is meaningless. It's just a statement about what choices we make as opposed to a statement about what's out there in the world. Okay, so to illustrate this point, I made up kind of a science fiction story. It's not a great story, but at least it's better than Star Wars Episode 1. So here's my story. Okay, so suppose we're on the International Space Station, okay, and there's an American astronaut and a Russian cosmonaut, okay, and because they're in weightlessness, they can be in all different orientations. Okay, so suppose the American is like this, and the Russian is like this. Okay, and so they observe the same thing. Okay, so let's suppose that they are both studying an Apple Pencil. Okay, and so here's an Apple Pencil, which is moving with some velocity like this. Okay, and so they can each make statements about their observations of the Apple Pencil. Okay, so the American say he observes it and he says, well, the y component of the velocity is positive. Okay? And then maybe the Russian observes it and he says, oh, well, the y component of the velocity is negative, okay? So they get into a big fight, right? They say it's positive, no, it's negative, right? So it starts a war or something. Um, so, but of course, they're observing the same Apple Pencil, right? They're observing the same motion of the same object. They're just describing it in different ways. Okay, so now we have to say, well, you know, what can the American and the Russian agree on, right? Well, they both like Donald Trump. Okay, so what else can they agree on, right? Well, let's make a table here. Oh, here I have to start my sharing. Okay, so I start my sharing. Okay. Okay, so the question is, what can they agree on? That is, what is independent of their choice of coordinate system? Right? Well, one example is they can agree about the magnitude of vectors. Okay, so suppose they each measure velocity. Okay, so one of them measures a set of numbers, Vx, Vy, Vz. Right? The other one measures a set of numbers, Vx prime, Vy prime, Vz prime. These numbers are all different from each other. Okay? But then maybe they go to calculate the magnitude of the velocity vector squared. Okay, so that is one of them calculates Vx squared plus Vy squared plus Vz squared. And the other one calculates Vx prime squared plus Vy prime squared plus Vz prime squared. Okay, and then they say, whoa, these things come out equal, right? Even though we had, one set of three numbers over here and another set of three numbers over here, when you square the numbers and add them up, you get the same thing. Okay, so the word for that is that this is a scalar, which is a quantity that does not depend on the choice of coordinates. And this works basically thanks to the Pythagorean theorem, right? That the Pythagorean theorem shows that this sum of squares is the length of a hypotenuse squared, and this is the length of the same hypotenuse squared. Okay. Incidentally, if they take the fourth powers and add them up, they probably don't get the same number. Vx prime to the fourth plus Vy prime to the fourth plus Vz prime to the fourth. These things are normally not equal to each other. And that's because there is the Pythagorean theorem for squares, but there's no Pythagorean theorem for fourth powers, right? It only works for squares. Okay, so that's one thing they can agree on. What else can they agree on? Another thing is dot products. Okay, so suppose they measure two vectors. Okay, so they measure velocity, that's one of them. So that is Vx, Vy, Vz versus Vx prime, Vy prime, Vz prime. Okay, and they'll measure a force, right? Some other set of numbers, Fx, whoops, no prime, uh, Fx, Fy, Fz versus Fx prime, Fy prime, Fz prime. Okay, so these are all different numbers, right? If they each make a table in their own lab notebook of what numbers they observe, they all come out different from each other. Okay? But they could combine them to get the power of F dot V. Okay, and so for one of them, it's Fx Vx plus Fy Vy plus Fz Vz. And the other one measures Fx prime Vx prime plus Fy prime Vy prime plus Fz prime Vz prime. And then when they combine the numbers in this way, they say, whoa, those things come out equal also. Okay? So this is another example of a scalar, that is a numerical quantity that does not depend on the choice of coordinate system. Of course, the first thing that I showed you is a special case of the second one because it is a dot product of just V with itself. So this is a second thing that they can agree on. Now, there are more examples. Okay, so let's make up another more complicated example. Suppose we think about vector equations. Okay? So suppose they each measure the force F and the acceleration A. Right? They each have their own set of numbers for that. Right? Then they both want to check and see, does Newton's second law work? Okay, so Newton's second law says F equals ma. Okay, so this is a vector equation. So that means for the coordinate system of one of them, Fx is max and Fy is may and Fz is maz. So one guy checks that those things are all true. Okay, and then the other guy checks Fx prime compared with the mass and Ax prime. Fy prime is the mass times Ay prime. Fz prime is the mass times Az prime. Yeah, that works too. Okay, so even though they each have different sets of numbers for the force and different sets of numbers for the acceleration, still the same vector equation works for both of them, right? The same vector equation works in any coordinate system. Okay, now let's get to another example. Okay, so suppose they want to measure something about dielectric properties. Okay, so they have this Apple Pencil and they do an experiment where they apply an electric field to the Apple Pencil and they measure the electrostatic polarization. So they both observe the same experiment being done, okay, with an electric field and a polarization. Okay. So now they want to check the prediction that the polarization is a certain matrix, polarizability, dotted with the electric field, okay? So that is, if I write it out in components, that Px, Py, Pz is a matrix multiplication, alpha x, x, alpha x, y, alpha xz, then alpha yx, alpha yy, alpha yz, alpha zx, alpha zy, alpha zz, right? The matrix product of that with the electric field. Each of the astronauts observes that this equation is true, just as each of the astronauts observes that F equals ma is true. But they each observe their own set of numbers to go here, and their own set of numbers to go here, and their own set of numbers to go there. So they don't agree on any of the numbers, but they do agree that this equation is true, or this equation is true, with each having their own individual set of numbers. Okay. So this is also an equation which does not depend on the choice of coordinate system, just as F equals ma is an equation which does not depend on the choice of coordinate system. The way that that can work is that each of the pieces in this equation is describing some three-dimensional object in space, right? It's describing some properties of the Apple Pencil in the experiment, okay? That this is a vector, right? It's a set of three numbers, but it's not just any old set of three numbers. It's a set of three numbers which together describe a real thing, the electric field. Right? Likewise, this is another set of three numbers, which is not just any old three numbers, but it describes a real thing, which is the polarizability, or the polarization, excuse me. And then this set of nine numbers, likewise, is not just any old nine numbers that are thrown together, but it's nine numbers that describe a different kind of three-dimensional object. And that sort of object is a tensor, right? It is a way of describing a sort of three-dimensional object, which is a real three-dimensional object oriented some way in space, but it's not a vector. It's a different kind of three-dimensional object, a higher order three-dimensional object, which expresses the relationship between these two vectors. So this is an example of a tensor. Okay, it's an example which shows that you can't just throw together any nine numbers, right? But it has to be nine numbers that describe an actual three-dimensional object. Now, you might ask, how can we tell the difference between a set of nine numbers that describes a three-dimensional object versus any old set of nine numbers? The answer is that if they describe a three-dimensional object, then they have to change in a certain way when you change coordinate system. So, whoops, that is, when you change coordinate system, the vector has to change in a certain way. I'll say the vector components change in a certain way. And likewise, the tensor components change in another certain way. And the way that these things change, they all sort of fit together, right? And they fit together in such a way that this equation can be true in any coordinate system, not just in one coordinate system. Ibrahim, you have a question?
Yeah. So suppose should I have the physical system in Cartesian coordinates, or I can represent a tensor in Cartesian or polar coordinates as well?
Excellent question. Um, the there there are two answers to that. Okay, there are two answers to that excellent question. One is that what I am going to teach you in this semester is just one Cartesian coordinate system to another Cartesian coordinate system. That is, you have one set which is like this, and then another set's like this, and another set's like this, right? So there are many different Cartesian coordinate systems. And I am going to teach you about tensors which are expressed in a Cartesian coordinate system. And we will talk about how you change from one to another and how you make sure that the things that you write down don't depend on whether you do this versus that. A more advanced topic is, what if you don't want to use Cartesian coordinates at all? What if you want to use polar coordinates in 2D, or spherical coordinates in 3D, or cylindrical coordinates in 3D, or anything else? Physics doesn't depend on those choices either, right? And so it is possible, for sure, to describe tensors in any non-Cartesian coordinates as well. But that is a more advanced topic, which I love, but I'm not going to get into in this semester. But after this is done, if any of you want to talk about that, I would be very happy to discuss that with any of you. It's a great subject, but it's just beyond the scope of this course. Okay, thank you for that. Okay, so we're just going to be talking about.
Jonathan,
Please, yes, Mr.
so I mean, the examples you gave here are just some examples of I mean, first law of general theory of relativity.
I'm sorry, say the question
I
again,
mean,
please.
not a question. I mean, the examples you told us here are just some examples of first general theory of relativity.
So you're asking about this compared with the general theory of relativity?
Yes.
Yes. Um, right. So that's a related point, right? And so you know, this kind of consideration was important for Einstein, right, when he was working out the general theory of relativity, right? And he also wanted to compare different possible viewpoints, and he got into a more general consideration, right? He was thinking about um, how does something look, for example, to a person who's accelerating upwards in an elevator, right? What if you have an elevator that's going faster and faster going up, right? And that person would observe objects falling to the floor of the elevator, right? And so Einstein's point of view was that this looks just like gravity. And so he developed a theory of gravity so that gravity would look like acceleration. And in order to do this, he had to consider transformations between different kinds of coordinate systems. So that's related to Ibrahim's question about how do you change from one coordinate system to another one. That is another great subject, which is beyond the scope of this course. Okay, and so I will only talk about transformations between, some guy with his head like this versus the guy who's tilted over, right, with a different Cartesian coordinate system. All right, you have to begin somewhere. I'm going to begin with that. Okay, great points. So, whoops. So the point that I was saying here, right, is that the way you tell the difference between a tensor versus any old set of numbers that somebody's just thrown together in a table is, how the numbers change if you change coordinate system. Okay. So that is the reason why books about tensors make a big deal about what happens in a change of coordinate system. This is one point that really confused me when I was a student, right? When I was a student, I read all these books that made such a big deal about the change of coordinate system. And I thought, well, okay, maybe I need to do that once in a while, but I don't need to change coordinate system that often. So why is there such a big deal about it? Right? And the big deal isn't that you have to do it often. The big deal is it is possible in principle to do it. And that is what makes the difference between a tensor versus any old set of numbers. Professor Palfy used to have a handout about tensors that he gave out, which began with the sentence that a tensor is a set of numbers that transforms as a tensor. Can I ask the second years, does he still have that? Any of you seen that thing? No, maybe not. You haven't seen what I'm talking about. Never mind. It was just a sentence which sounds like poetry in some sense. And it expresses this idea, right? That the numbers in a tensor have to follow a certain transformation rules. But because we don't have to do these transformations very often, I'm not going to emphasize those things here. Instead, I want to make this more of a practical lesson about how to work with tensors. And I am just going to tell you some rules for how to work with tensors. And the point of my rules is that if you follow my rules, you will make statements that are physically meaningful in that they don't depend on a choice of coordinate system. Whereas if you break my rules, then you will make statements that are physically meaningless in the sense that they depend on which coordinate system you use. So you'll be saying things like, the temperature is less than my age, and you don't want to do that. Okay, so let me tell you some practical things about working with tensors. And I'm going to tell you these things without proofs. I'm just going to tell you the rules, and then later on I'll say more about the transformations. Well, actually, even before I start talking about working with tensors, maybe I'll warm up by talking about working with vectors, because these things are sort of familiar to you from what you've done in previous math classes. And this will help you to warm up for the generalization to tensors. Okay. So let's first think about notation. So the notation, right? We often will think about a vector as some abstract 3D object. And so if I am writing that with a pen, I usually write a letter with an arrow over it. Okay. Some people, a sort of old-fashioned notation is to write a letter with an underline under it. You might see in some books. In a printed book, it's often written in boldface. So it would be like V, like that, which is how it looks in my book, but I can't do that with a pen very easily. Okay, so this is a vector as an abstract 3D object. All right. Now, and so that's one kind of notation. A second kind of notation for the same thing is to expand in terms of basis vectors. So conventionally, we define basis vectors that are along the x-axis, along the y-axis, and along the z-axis, right? So we might write a unit vector along the x-hat is x, along the x direction is x-hat, and a unit vector along the y direction is y-hat, and a unit vector along the z direction is z-hat. Okay? And so this little hat symbol above the vector means that it's a unit vector, right? That x hat dot x hat equals 1. Okay? And so if I want to write any old vector in terms of these basis vectors, I would say vector v is some vx times x hat plus vy times y hat plus vz times z hat. And then these coefficients are called the components of the vector in the XYZ coordinate system. Okay, so this is a perfectly good way of writing the abstract vector v, right? That this means the same thing as that, right? They're two equivalent representations of the same object. Okay, a third possibility is that we can list the components in a column. So we could write V equals Vx, Vy, Vz. Or we could list them in a row. So V is Vx, Vy, Vz. So this is a general expression for the vector, which emphasizes the set of three numbers. That's fine, as long as we recognize that those are not any old three numbers, but that is a representation of this 3D object. Right? And then we could say there's an index notation for any component. That is, we could write V sub I, where I is an index that can represent X, Y, or Z. Or sometimes people would put that numerically and say I is 1, 2, or 3. It means the same thing. Right? This is useful for writing vector equations. Right? That is, if we have the general vector equation that V is 2 times U, right? That's a relationship between the vector V and the vector U. Right? We could write that equation in terms of its components as Vx is 2 times Ux, and Vy is 2 times Uy, and Vz is 2 times Uz. Right? So this is an equation for the components. It's really 3 equations for the components. That is fine, but it's a lot of work to write it out. Okay? So the index notation is more compact than that. Right? The index notation is to say Vi equals 2 Ui. So this equation has to be true for all I. So that is I equals X, and it is true for I equals Y, and it is true for I equals Z. So this equation in the box means the same thing as those 3 equations all written out, right? This is 3 equations in one. Right? Sometimes people write for all I after that, but usually people leave out the for all I. Usually people don't bother to write it, but you should still think it, right? It is implicit in writing this equation that it is true for all I. Even if people don't write it, they still mean it. So this is 3 equations in one for I equals X, Y, and Z. Okay, now let's see if we can do the same things for tensors. Okay, so for tensors, right, working with tensors, okay, the kind of notation we use has the same sorts of choices. Okay, so we could think about an abstract tensor. And this is something that I might write as a T with a double-headed arrow over it. Yeah, as a T with a double-headed arrow. Or the same people who put underlines on vectors might put 2 underlines under a tensor like that. In a printed book, it would also be written in boldface. So it would be like T, it's really thick letters like that. So it would look in a book the same as a vector, right? When you see something in boldface, you can't tell whether it means a vector or a tensor. You have to figure it out from context. Okay, but right now, for these classes, I will write it like this with the double-headed arrow, and unless, of course, I forget, and then you can remind me. All right, now we could also expand in terms of basis tensors. So the same way that people expand a vector in terms of basis vectors. We could say that the tensor T as an abstract object is Txx times x hat plus Txy x hat, y hat, right? So each of these things is a basis tensor, which means some input comes in the y direction that gives some output in the x direction, right? It's input on the right, output on the left. And then I'm not done yet, right? I have to write plus Tx x hat, z hat, plus T y x y hat, x hat, plus T y y hat, y hat. You may notice this actually involves a lot of writing. People don't really do this in practice. I'm just saying, in principle, we could write things this way. And I do so once a year in order to show students, but nobody really does this in real life. Plus T, Z, Z, Z hat, Z hat. Okay, so in principle, you could do all that, but it doesn't happen very often. As a third possibility, we could list all those components. In a matrix. So instead of writing out all this stuff, you could say, well, the same as I want to highlight 3 vector components, I could highlight these 9 tensor components. So I'll write them in a matrix. Okay, so I could say the abstract tensor T is txx, txy, txz, tyx, tyy, tyz, tzx, tzy, tzz. Okay, so this is also a possibility, right? So a matrix to write out those 9 numbers. Or a fourth possibility is this index notation. That is, you can write Tij, where I and j are both indices. So I equals x or y or z, and j equals x or y or z. All right, so this symbol T sub ij might mean any of these 9 components, right? Depending on which thing I put in for I and which thing I put in for j. Okay. So this could be useful for writing a tensor equation. All right, so for example, suppose we want to say that the tensor T is 2 times the tensor S. So it's a relationship between 2 tensors. I could write this out component by component, right? So I could write Txx is 2Sxx. Txy is 2Sxy. Txz is 2Sx. Well, that's 3. I got 6. Oh man, I don't have to do all these, do I? Okay. So there are 9 things to write out. Okay. A nice compact way to write all 9 of those things is to say Tij is equal to 2Sij. So this thing is 9 equations in one. Right? This thing has to be true for I equals x and j equals x, or for I equals x and j, and for I equals x, j equals y, and for I equals x, j equals z, and for I equals y, j equals x, etc. Right? It's 9 equations in one. Right? So this is true for all I and all j. So sometimes people would say this explicitly for all I and for all j. But normally people don't bother to say it, but it's still implicitly true. Okay, so people always mean for all I and for all j, even if they don't explicitly say it. Okay, so this leads us to what I will call rule number 1 of my rules for working with tensors. Okay, rule number 1 is if an index appears once in some term it must appear once in every term on both sides of an equation. Okay. So, this is, one example of that rule, right? So there's an index I that appears once on the left side, and it appears once on the right side. J appears once on the left side, and J appears once on the right side. Okay, we could say more generally, Tij is 2Sij plus 3Rij. Okay? So here, the index I appears once in this term, and this term, and this term. And it appears once in this term, and this term, and in this term. Okay, so this is good, right? This passes my rule. On the other hand, if we write out Tij is 2Sij plus 3Pi. This is terrible, right? This is terrible because there is no J in this term, okay? And so this is not the kind of equation where we can say, oh, this has to be true for J equals X or Y or Z. Okay? So this equation violates rule number one. So this equation, it will turn out to involve a particular choice of coordinates. Okay, it will not be true in all coordinate systems. It might be true for one observer in one coordinate system, but if another observer looks at it in a different way, he will not find this equation to be true. So you don't want to write equations like this second thing. Don't do it. Okay, you want to write equations like this first thing. Okay, and in equations like this, people say that the word for this is I and J are free indices. So indices is the plural of index, okay? And to say that they are free means they get to be X or Y or Z, whatever they want. Well, they get to be all of these things, right? They are all of these things, and they can be all of these things in every term on both sides of the equation. Okay, so that is rule number one. And I am out of time, so I will stop with this rule and I'll get on to the next rule number 2 and number 3 on Friday. Okay, I'll stop here and answer any questions. Thank you all.